All right, welcome everybody. Today we're going to talk about lesson number 45, and we're actually going to kind of jump off the unit circle a little bit. We're going to go back and talk a little bit more about what it means to be a radian, something called linear speed, and something called angular speed. The content from today's lesson isn't so much an AP topic, it's actually more of a physics connection. So depending on your familiarity with physics topics, some of this stuff might be familiar. So first, let's go back to the idea of what it actually means to be a radian. I've kind of been using this word, telling you that you could measure quantities and angles in radians. We've talked about pi over 2 radians and 3 pi over 4 radians, but I really want you to have an idea of what it means to be 1 radian. So in general, the radian measure of the central angle of a circle is the number of radius units in the length of the arc that it intercepts. When we talk about arc length, the variable that we're going to use is s. And when we're talking about the value of a radian measurement, we're going to use the theta. So if you wanted to calculate the measurement of any radian unit, you're going to measure the length of the arc, which is s, divided by the length of the radius. When you're talking about an angle where the length of the arc is exactly equal to the length of the radius, then that's how you get exactly 1 radian. If you try to divide the length of the arc s by the length of the radius and you get more than 1 radius length, you're going to have a measurement greater than 1 radian. And if you get less, you're going to have a measurement that's less than 1 radian. But again, if the length of the radius is exactly equal to the length of the intercepted arc, that's exactly 1 radian, and then it will be bigger or smaller accordingly. Keeping that in mind, in the unit circle, so again, now we're on the unit circle, of course, there are 2 pi radians in the entire circle. Typically known as 6.28 radians if you were to find the decimal equivalent. I know that the AP strategy is to round to 3 decimal places, but for some reason, whenever people talk about the measurements rounded in decimals on the unit circle, they tend to use 2 decimal places, but either one would be acceptable. So because of the fact that there are exactly 2 pi radians in the entire circle, that means there are a little bit more than 6 radians total. So let's talk about where those radians would be. Again, let's assume that the length of the unit circle radius is here in red. When you turn through an angle such that the length of the intercepted arc is exactly the same as the length of that radius, that's why you would have a measurement of 1 radian. Then let's say you have an arc where you could fit exactly 2 of these radius units rather, that would be exactly 2 radians. Then if you had an arc where you could put 3 radius lengths, that would be 3 radians. And of course, notice that that's just shy of pi, which would be 3.14. Then 4 radians, 5 radians, and 6 radians would always just be a little bit shy of 1 full revolution. These values do not change in the same way that pi over 6 is always in the same location. 1 radian is always in the same location. So what this means is I could now say to you, draw for me 1 radian or 2.5 radians or -3 radians. And you should be able to have some concept of what the length of 1 radian is in terms of an angle measurement. So then if we're just looking at the quadrantals, since those kind of seem to be our signposts. So again, let's say you started at 0 and you started moving in standard position. Pi over 2, the decimal equivalent is 1.57 radians. Then 3.14 radians. 4.71 radians would be 3 pi over 2. And then 1 full revolution of 2 pi would be 6.28 radians. And then this final slide just kind of puts them all together here, showing you the relationship between those unit circle values and then 1, 2, 3, 4, 5, 6 radians. Another way you can kind of use to help you estimate is at the bottom. You know, of course, that if you're trying to convert between degrees and radians and vice versa, you're going to either multiply by pi over 180 or 180 over pi. What those conversion factors tell us is that 1 radian is equal to approximately 180 over pi, which is approximately 57 degrees. So again, going forward, if I say to you, sketch 2.5 radians, you are sketching 2.5 times 57 approximately. And then by a similar token, 1 degree would be equivalent to approximately pi over 180 radians. So again, these are all radians, whether they have pi's or not. And from this point forward, you should be able to sketch a radian angle no matter which of those values I give you. So now that we're a little bit more familiar with what a radian is, here's something else that we can do with it. So again, this is the formula for determining a radian measurement. You're going to divide the length of the intercepted arc by the length of the radius. If you go ahead and cross multiply, you're going to get that S equals R theta. And this is the formula for the length of an arc, also known as arc length. So again, what that's saying is that if you want to find the length of this S, you're going to multiply whatever the radius of the circle is. Again, may or may not be on the unit circle, multiplied by whatever this central angle is. Keeping in mind that when we do these problems, something very, very important here, the formula is only going to work if theta is in radians. So if radians is given to you in degrees, you have to first convert it. So here's our first example. A circle has a radius of 4 inches. Find the length of the arc intercepted by a central angle of 240 degrees. So the first thing you're going to want to do is you're going to want to take that 240 degrees and you're going to want to convert it to a radian measurement. Now, the truth is you should kind of already know what 240 degrees is equal to now that we've been looking at the unit circle for days and days. Kind of a shortcut, other than just memorizing it, is 240 divisible by 60? It is how many times? 4. Well, 60 is pi over 3. 4 times 60 is 240, so that would be 4 pi over 3. If you still can't remember, you could multiply by pi over 180 and then reduce. Either way, you're going to get a value of 4 pi over 3. And again, yes, you're going to have your unit circle in front of you, so you could just look at it. But again, imagine that you were under a circumstance where you wouldn't have those conversions. You would have to somehow be able to find 4 pi over 3. So S is equal to R theta. So S is equal to 4 times the angle, which is 4 pi over 3. As long as the value multiplies nicely, I would just leave it. So this is 16 pi over 3, and then it does have to have a unit, which in this case is inches. Again, you could convert that to a decimal if you wanted to, but really no need unless there is some other decimal in the problem. How about something like example 2? The second hand of a clock is 18 inches long. And the reason why that's important is because the second hand of the clock, that of course is approximately equal to only halfway around the circle. So that's the radius. Okay, so that's good to know. In 25 seconds, it sweeps through an angle of 150 degrees. How far does the tip of the second hand travel in 25 seconds? So again, if you remember from the previous slide, 150 degrees is no good. 150, how could you know just off the top of your head what value that is in radians? Well, it's not divisible by 60, but it is divisible by 30 5 times. So 5 times 30 is 150. 5 times pi over 6 would be 5 pi over 6. Again, whatever you have to do to get that conversion, do it. So S is going to be equal to R theta, which is going to be 18 times 5 pi over 6. 18 divided by 6 is 3. 3 times 5 pi is 15 pi. So S equals 15 pi, and we are again in inches. So just make sure that if it's a word problem, which most of today is going to be, make sure that you have an appropriate unit. In addition to finding the length of a radius, and in addition to finding an arc length, there's a couple of other things that you can find, which we'll get to in a minute. But here in example 3, a record with a diameter of 12 inches turns at 33 1/3 revolutions per minute. Find the distance in feet that a point on the rim travels in 1 minute. So as these problems get a little more complicated, there's a few things you want to watch out for. Here, they're telling you how fast in minutes, and they're asking you about minutes, so that's good. Here, they're giving you inches, and they're asking you about feet, so at some point, you're going to have to do a conversion. And then finally, they give you a radius, or they give you a diameter, and you need to find the radius. A radius is, of course, half the diameter, so the radius is going to be 6 inches. To kind of clean things up and make it a little bit easier, 33 1/3 revolutions. I'm going to go ahead and make that into a 100 over 3. Just makes it a little bit nicer instead of having that weird 1/3. So S is equal to R theta. And a little bit more complicated in this case. So S is equal to, so R is 6 inches. And then in terms of the theta, so they're telling you that it turns at 33 1/3 revolutions per minute. So that means it goes all the way around 100 thirds times. How far is it going around every time it does a full revolution? Well, because we're living in a world of radians, it goes 2 pi every time it goes all the way around. So to actually find the angle, you're going to have to multiply 100 thirds times 2 pi. And again, that's because going just once around is 2 pi. If you go 100 third times around, you have to multiply them. So 6 divided by 3 is 2. 2 times 100 is 200 times 2 pi is going to give you 400 pi inches. And then finally, they actually want this in feet. So you're going to have to convert it to feet, which means you're going to have to divide by 12 inches. There are, of course, 12 inches in a foot. If you go ahead and reduce 400 by 12, you're going to get 100 thirds pi, and then your final answer is going to be in feet. So hopefully you know there are 12 inches in a foot, 60 seconds in a minute. Those are the kinds of things that, hopefully you just have a working knowledge of. So again, after you have found an arc length and after you have found how to calculate the radian measurement, you're going to be asked to find linear and angular speed. So again, this is really where that physics connection comes in. So consider a particle moving at a constant speed along a circular arc of radius r. You could be asked to find the linear speed, which is how fast the particle is moving. That is denoted with the letter v. It's equal to the arc length divided by time. And again, arc length is represented by the letter s. Notice that when you're talking about a linear speed, you're talking about how fast something is moving along the outside of a circle. When you're talking about angular speed, that's how fast the angle is changing. It has to be the central angle, and you have to then divide it by the time. The central angle is going to be denoted with a theta, because again, we're going to be in radians. And then this Greek-looking W, that's a psi. So again, it's just another variable that they happen to use. And again, you're always going to be talking about angular speed, how fast that central angle is changing. Something that we now kind of want to look and consider here for the linear speed formula. So V is equal to S over T. If you remember, S is arc length, and arc length was equal to R theta. So we're going to make that replacement. If you then look at V being equal to R theta over T, and the fact that W or psi is equal to the angle over T, you could further conclude that V is equal to R times whatever psi is, or psi times whatever r is. So this is a simplified version of the equation that you should use if you already know the angular speed. If you don't already know the angular speed, then you should use r theta over t. So again, two different versions of linear speed depending on how much information you know, and then one formula for the angular speed. Probably is a little bit easier than it seems once we go ahead and try to actually put it into action. So a Ferris wheel with a 50-foot radius makes 1.5 revolutions per minute. Find the angular speed in radians per minute and the linear speed in feet per minute. So something that you want to watch out for. So minute, minute, minute. As long as there are all the same unit, in this case minutes, you can just assume that the value of time is 1, as in 1 minute. You only have to put in some value for time if you're converting between two different units. So when it comes to A, we're talking about angular speed. So again, you're going to use that psi, which is kind of a fancy looking W. That is going to be equal to the central angle divided by time. Again, time you can just leave as a 1, which means you can just disregard it because we're all in minutes. So when we're talking about the angle, you have to talk about how far the angle, or how much the angle changes in 1.5 revolutions. So 1.5 revolutions, how far around does a circle go in 1 revolution? Well, that's always 2 pi. So the total angle that is covered is 1.5 times 2 pi. And again, time would just be 1, which you could put or not put. It's up to you. So 1.5 times 2 pi would give you 3 pi radians per minute. Remember that an angular speed has to have an angular unit. So when they say radians per minute, they're telling you how large the angle is. Then for part B, you're looking for the linear speed. Because of the fact that you already did the angular speed, you can just find V by multiplying the radius times the angular speed. So that would be 50 times 3 pi that we already found, which would give you an answer of 150 pi. And here you're talking about a distance, which is feet per minute. And again, we know that because you're talking about feet, and all the different units agree. Again, leave it in terms of pies, I would, unless there is some other decimal that needs you to give your answer as a decimal. Example 5, the second hand of a clock is 10.2 centimeters long. Find the linear speed of the tip as it passes around the clock in centimeters per second. So the fact that we are talking about centimeters and centimeters, but because of the fact that we're talking about per second, we're going to go ahead and talk about 60 seconds in a minute, because we know that in 1 minute it goes all the way around. So we are going to go ahead now and talk about the linear speed. Because I don't actually know the angular speed yet, I'm going to use that V equals S over T, which is R theta over T. The length of R is 10.2. Then 2 pi, because it's 1 revolution, divided by 60 seconds. And again, this 2 pi comes from the fact that it goes once around in 1 minute, but because we want to convert it to seconds, that's why we have to divide by 60. Because there is a decimal in this problem already, it probably makes sense to give your final answer as a decimal. So very carefully, you would do 10.2 times 2 pi, first hit enter, and then divide by 60. That would give you 1.068. We're talking about centimeters, and because we converted it to seconds, that would be 1.068 centimeters per second. One last one of this type. So you have a circular blade of a saw that rotates 2,400 revolutions per minute. Find the angular speed in radians per second, and then find the linear speed in inches per second. So we have a minute, we have a second, we have a second. Again, because of the fact that you're converting, you are going to have to go from minutes to seconds, which means divide by 60. So starting with the angular speed, again, that's the fancy W. So the angular speed, you're going to go ahead and divide the angle by the time. So the angle, it goes 2,400 revolutions per minute. And then again, 1 revolution is 2 pi. Because you're changing from minutes to seconds, that's why you're going to go ahead and divide by 60. 60 goes into 2,400 40 times 2 pi is going to be 80 pi radians per second. And then for part B, for the linear speed, again, because we already have the angular speed, you're just going to multiply the length of the radius, which is 4, times whatever your answer from part A was, which is 80 pi, which is going to give you an answer of 320 pi, and the unit is going to be inches per second. And finally, that brings us to the last formula of the day, and it has to do with finding the area of the sector of a circle. So a sector of a circle is the region bounded by 2 radii of the circle and their intercepted arc. And the formula says for a circle with radius r and central angle theta, then the area of a sector is found by the following: 1/2 the radius squared times the angle. And of course, the angle must be in radians. So again, everything from today, the angle has to be in radians to start. If it's not, you have to first convert it. So some examples with this: a sprinkler on a golf course is going to spray water over a distance of 75 feet and rotate through an angle of 135 degrees. Find the area of the fairway that is watered by the sprinkler. If you kind of have seen a sprinkler like this, it basically is attached and then it pivots. So here's where it would start, and it would pivot through some degree, and it would make some sector of a circle, some part of a revolution. It doesn't go all the way around. So they're telling us that 75 feet is the length of what would be the radius of the circle, and then it rotates through 135 degrees. Now, of course, 135 degrees, we would have to convert that to a radian because it's a multiple of 45. How do you get it? It's 3 times 45, which is how I know this is 3 pi over 4. Again, you are going to have to do these conversions by any means necessary, but the sooner you're able to do them quickly and without a reference or a calculator, really the better off you're going to be in the long run. So to find the area, again, it's 1/2 r squared times the angle in radians. So in this case, it's 1/2. If you square 75, you're going to get 5,625 times the angle, which is 3 pi over 4. If you multiply all the constant values, you're going to get 16875 over 8, and that's times pi. Not a great looking fraction, so fine to leave it, of course, but if you want to go ahead and round it, it would be 6626.797, rounded to 3 decimal places, and in this case, because it's part of an area, it would be square feet. So as you've kind of seen today, all of these problems today involve formula, so it's really just a matter of having the correct formula and then putting the values in the right slot, of course, ensuring that you're in radians throughout. A couple more, you're working at a pizza delivery store and your math teacher calls. They want a large 15-inch diameter pizza with pepperoni on just 36-degree slice of that pizza. What is the area of the pizza that will have pepperoni on it? Obviously, a perfectly normal order for a normal person. So if you're talking about one slice of pizza, you're talking about the fact that it's a 15-inch diameter pizza. So that, of course, would mean that the radius of a slice would only be 7.5. 36 degrees. I'm going to go ahead and convert that by multiplying by pi over 180. That reduces to pi over 5. Just FYI, if it does not simplify to be a nice value of pi, you can just round it to 3 decimal places. Even if it doesn't wind up being a nice value with a pi, you can leave it anyway. Just keep in mind that every time you round along the way, your answer gets ever so slightly farther away from the answer that I will have. But again, as long as you have all your work, it's fine. So the area of this pizza slice is equal to 1/2 times r squared times the angle, which is pi over 5. Because of the fact that you have a decimal in it already, I would probably just go ahead and put that entire thing in my calculator, giving you 17.671. And again, because it's area, it would be square inches. Final problem has to do with a windshield wiper. So on a vehicle, one windshield wiper is 60 centimeters long, and it's attached to a swing arm, which is 72 centimeters long from pivot point to tip. Next time you're in the car and you're looking out at your front window at the windshield wiper, the arm itself, the wiper is not attached the entire part. It's only attached for the part that it wipes. So what they're telling you is that the length of the entire arm is 72, and then they're telling you that the length of the wiper itself is only 60. You're saying that the arm swings through 105 degrees. What area to the nearest square centimeter is swept by the wiper blade? So because of the fact that you're only trying to find the area of the portion that is actually being wiped, you have to find the area of the entire arm, and then you would have to subtract the region that is not actually being wiped. So again, this is still an area problem of a sector. So 1/2 r squared times the angle. In a case like this, 105 degrees. So 105 degrees, if you multiply that by pi over 180, it reduces to be 7 pi over 12. So again, we're going to start by finding the area of the entire region of the pivoted arm. So that would be 1/2 times 72 squared times 7 pi over 12. Then we would subtract off the part that we don't want. So the part that we don't want is here. That's not actually wiping anything. So if the entire distance of the arm is 72 and then you're only wiping the 60 centimeters, you're going to subtract off that region that has a radius of 12. From here, you could plug it in if you wanted to make the calculation ever so slightly easier. You could factor out the greatest common factor, which would be a 1/2 at a 7 pi over 12 from each term, which is essentially 7 pi over 24. If you factored out 7 pi over 24, you would be left with 72 squared, which is 5184, minus 144. If you were to then go ahead and multiply those out, you would get 4618.141. That would be centimeters squared. And then because they're saying to the nearest square centimeter, again, maybe your book might say that, although the AP test will not really ever. So you could just say 4618 cubic centimeters, or I'm sorry, square centimeters. Either one is fine. Again, as always, as long as you show the work, you should be good to go. So you're going to go ahead and do homework 45 tonight, which is in the book. Don't be alarmed the fact that it's section 4.1. We've kind of been jumping around through all of chapter 4, and actually we've actually already done some of chapter 5 and 6. So don't be concerned with us necessarily going in the right order. So that'll do it for lesson 45. So thanks very much for tuning in, guys, and we will catch you next time.